The universe has a way of keeping even the brightest minds humble. Just ask the scientists who first detected the rhythmic pulses of a distant celestial object in 1967. At first, they thought it might be a signal from an alien civilization, a cosmic SOS beaming across the void. But the truth was even stranger. They'd stumbled upon the first known pulsar, a rapidly spinning neutron star so dense it defied all expectations. That moment of shock, when certainty dissolved into wonder, wasn't an exception. It was a glimpse into a universe that thrives on the unexpected, where even the experts are left wide-eyed and speechless. Imagine dedicating your life to unraveling the secrets of space, only to witness something so baffling it rewrites the textbooks. That's the reality for astronomers and physicists who have faced the cosmos's greatest curveballs, from black holes that shouldn't exist to eerie signals that vanish before they can be explained. These aren't just scientific oddities, they're reminders that the universe operates on a scale of mystery we're only beginning to fathom. And today, we're diving into 25 of the most jaw-dropping moments in space exploration, where the unimaginable became undeniable. Picture this, a team of researchers tracking a faint radio whisper from deep space, only to realize it repeats in a pattern that feels almost intentional. Or a telescope capturing a galaxy so ancient it shouldn't have had time to form, forcing scientists to question the very timeline of the cosmos. These aren't scenes from science fiction, they're real discoveries that left even the most seasoned experts scrambling for answers. From rogue planets wandering without stars to cosmic explosions brighter than entire galaxies, the universe has a flair for the dramatic. And as we unravel these mysteries together, you'll see why space remains the ultimate frontier, a place where every answer leads to 10 new questions and where the only certainty is astonishment. Strap in, because what comes next will leave you seeing the stars in a whole new light. One night in August 1977, a radio telescope in Ohio picked up a signal so extraordinary that the astronomer who discovered it circled the printout and wrote one word in red ink: "Wow." The 72-second burst of noise came from the direction of the constellation Sagittarius, blasting 30 times louder than the background static of space. What made it electrifying wasn't just its strength. It matched the exact frequency scientists predicted an alien civilization might use to broadcast its existence. Hydrogen's natural wavelength, 1420 MHz, is famously quiet, like a silent channel between radio stations. So when the Big Ear telescope caught a screaming siren on that dead air frequency, researchers froze. The team scrambled to rule out earthly interference, no passing satellites, no military experiments, not even a stray airplane. The signal's intensity rose and fell like a cosmic sunrise, a telltale curve caused by Earth rotation sweeping the telescope's gaze across the source. It had all the fingerprints of a genuine transmission from the stars. Yet when astronomers turned every dish they could toward that patch of sky, the signal never repeated. Decades of searches yielded only silence, turning the wow signal into the ultimate cosmic teasers. Some theorize it was a comet's hydrogen cloud reflecting sunlight, but even that leaves gaps. The frequency was too precise, the duration too perfect. Others whisper about a one-time beacon from a distant civilization, a fleeting hello before vanishing back into the dark. What lingers isn't just the mystery, but the sheer rarity of the moment. In over 50 years of scanning the skies, nothing else like it has ever been found. The WOW signal stands alone, a 72-second enigma that reminds us how little we understand about the universe's quiet corners. It's the kind of discovery that makes scientists glance at each other over coffee, wondering if they'll ever get a second chance to ask, are we really alone? And for now, the cosmos keeps its secrets. Then in October 2017, astronomers spotted something streaking through our solar system that didn't belong, a needle-shaped object tumbling end over end, moving too fast to be tied to the sun's gravity. They named it Oumuamua, Hawaiian for scout, and what happened next shattered every expectation. Most speeding space rocks slowed down predictably, but Oumuamua did the unthinkable. It accelerated. The scientific community scrambled for explanations. Comets usually speed up when sunlight vaporizes their ice, creating a visible tail of gas and dust, but Oumuamua had no tail, no coma, nothing. Its acceleration was subtle but undeniable, as if some unseen force were nudging it forward. That's when Harvard astrophysicist Avi Loeb dropped a bombshell. What if Oumuamua wasn't a natural object at all? His theory that it might be alien technology, perhaps a solar sail catching cosmic winds, ignited a firestorm. Critics shot back, proposing exotic alternatives. Maybe hydrogen ice, invisible to telescopes, was evaporating and propelling it. Or perhaps Oumuamua was a shard of a shattered planet, its strange shape and movement unlike anything we'd seen before. But Loeb stood firm, pointing out that no natural model perfectly fit the data. The debate raged from observatories to Twitter feeds, exposing a rift in how science confronts the unknown. Was it reckless to consider alien origins or reckless not to? What made Oumuamua truly unsettling wasn't just its behavior. It was the realization that we might never know for sure. By the time telescopes could react, the visitor was already fading into the void, leaving behind measurements too scant for consensus. It became a Rorschach test for astronomers. Some saw a cosmic curiosity, others a missed opportunity to answer humanity's oldest question. The legacy of Oumuamua isn't just about one strange object. It's about how science grapples with anomalies, whether to stretch existing theories or dare to imagine something revolutionary. Because next time, we might not get a second chance before the mystery slips away. When the Kepler Space Telescope first spotted a star called KIC 8462852, nobody expected it to become one of the most baffling cosmic mysteries of the 21st century. Nicknamed Tabby's star after astronomer Tabetha Boyajian, who led its investigation, this seemingly ordinary flicker of light in the constellation Cygnus started behaving like nothing scientists had ever seen. Most planets dim their host stars by less than 1% as they pass in front, but Tabby's star didn't play by those rules. Its light would plummet by staggering amounts, sometimes 15, even 22%. As if something enormous and irregular were drifting between it and Earth. The dips weren't periodic like orbiting planets. They were chaotic, unpredictable, with no clear pattern to explain what could possibly block that much starlight. At first, researchers checked for telescope glitches, faulty data, anything to rule out an error, but the numbers held up. Theories spiraled from the plausible to the extraordinary. Maybe swarms of comets, shattered remnants of a planetary collision, or vast clouds of interstellar dust were to blame. Then came the idea that made headlines worldwide: alien megastructures. Specifically, a Dyson swarm, hypothetical solar panels built by an advanced civilization to harness their star's energy. The notion wasn't entirely fringe. Even astronomers quietly admitted it had to stay on the table when nothing else fully fit. Yet with every new observation, the mystery deepened. Spectrographic analysis revealed the starlight wasn't just being blocked, it was being absorbed unevenly, as if whatever stood in its way wasn't solid. Dust became the leading suspect, but even that explanation had holes. Why didn't the dust scatter shorter wavelengths of light as expected? And why did long-term studies show the star gradually fading over years, losing 3% of its brightness over just 4 years, a rate no known stellar behavior could explain? Tabby's star became a case study in how science wrestles with the unknown. Teams across the globe coordinated observations, crowdsourcing data from amateur astronomers to catch its next erratic dimming event in real time. Each new dataset chipped away at some theories while adding fresh layers of complexity. The megastructure idea faded, but no consensus took its place. Even now, with evidence pointing toward uneven dust clouds influenced by an unseen orbiting body, the star refuses to fit neatly into any box. What makes Tabby's star so compelling isn't just the lingering questions, it's how openly it humbles us. For all our models and telescopes, we're still decoding a universe that delights in defiance. This star, with its wild flickers and stubborn secrecy, reminds us that some cosmic puzzles aren't meant to be solved quickly. They're invitations to keep looking, keep questioning, and stay dazzled by how much we have left to learn. When NASA twin Pioneer spacecraft raced beyond the asteroid belt in the 1980s, engineers noticed something deeply unsettling. The probes weren't moving as they should. According to every known law of gravity, these trailblazers should have coasted smoothly toward the outer solar system, their trajectories as predictable as clockwork. But the data told a different story. An invisible force was tugging them backward, slowing their escape by nearly 300 miles per year. This wasn't a minor discrepancy. It was a deviation massive enough to rewrite physics textbooks, and it sent shockwaves through the scientific community. The Pioneer Anomaly, as it came to be known, became one of space science's most persistent riddles. Teams combed through decades of telemetry, searching for flaws in their calculations. Maybe radiation pressure from the probe's nuclear power sources was nudging them off course, or perhaps tiny gas leaks were acting like microscopic breaks. Others dared to consider more radical explanations: dark matter clumps distorting gravity near the sun, or even flaws in Einstein's theory of relativity itself. For years, every proposed solution crumbled under scrutiny, leaving researchers chasing shadows. Then came the breakthrough buried in the mundane details of spacecraft design. Pioneer's aging hardware, it turned out, was leaking heat unevenly from its radioactive power generators. That warmth didn't just dissipate into space, it bounced off the probe's dish antennas, creating a minuscule but relentless push in the opposite direction. When scientists finally modeled this thermal recoil effect in 2012, the anomaly vanished from their equations, case closed, or so it seemed, yet whispers of doubt lingered. Some physicists noted that thermal radiation couldn't account for every quirk in the data, leaving a sliver of the mystery unsolved. Others pointed to similar anomalies in other spacecraft, like the Rosetta probe's unexpected speed shifts near Earth. These lingering questions hint at something tantalizing. Even with the Pioneer case largely cracked, the universe might still be hiding deeper gravitational secrets, waiting for the next generation of explorers to uncover them. What makes the Pioneer Anomaly legendary isn't just the decades-long hunt for answers, it's the humility it taught us. Here was a glitch so small it could have been dismissed as noise, yet it forced scientists to question everything from spacecraft engineering to the fabric of spacetime itself. In the end, the solution came not from grand cosmic theories, but from the painstaking examination of mundane details most would overlook, a reminder that sometimes the universe whispers its truths in the language of subtlety. In 2008, astronomers made a discovery so unsettling it threatened to rewrite our understanding of the cosmos itself. While studying hundreds of galaxy clusters with NASA's Wilkinson microwave anisotropy probe, researchers noticed something impossible: entire swaths of the universe were moving. Not just drifting randomly, but streaming together at breakneck speeds toward a single point in space, like leaves caught in some invisible cosmic current. This phenomenon, dubbed dark flow, suggested something colossal lurked beyond the edges of our observable universe, a gravitational anomaly so powerful it was tugging galaxies toward it at over 1,000 kilometers per second. The implications sent shockwaves through cosmology. According to the Big Bang theory, the universe should expand uniformly in all directions, with matter distributed evenly enough that no single region exerts such a disproportionate pull. Yet here was evidence of a structure, or perhaps an entirely separate universe exerting influence from beyond the cosmic horizon. Some theorists proposed it could be a remnant of the chaotic conditions before inflation, a scar left from when spacetime itself was being stretched into existence. Others ventured even further, suggesting parallel universes might be brushing against our own, their gravity leaking through like shadows through a curtain. Skeptics countered that the measurements might be artifacts, subtle errors in interpreting the cosmic microwave background, the afterglow of the Big Bang that serves as a cosmic yardstick. But when independent teams replicated the findings using X-ray data from galaxy clusters, the mystery only deepened. The flow persisted across billions of light years, defying expectations that cosmic expansion should drown out such coordinated motion. Even more perplexing, the direction pointed toward a void, a region of space conspicuously empty of known superclusters or massive attractors. What makes dark flow so electrifying isn't just the scientific debate, it's the philosophical quake it triggers. If confirmed, it hints at a reality far vaster than we've dared to imagine, where our observable universe might be just one ripple in an infinite ocean of spacetime. For now, the phenomenon remains controversial, with newer studies both supporting and contradicting its existence. But whether it's a flaw in our models or a window into the multiverse, dark flow forces us to confront an exhilarating truth. The cosmos still holds mysteries that could redefine everything we think we know. The thin, rusty air of Mars holds a secret that's been taunting scientists for years, a whiff of methane that comes and goes like a ghost. NASA's Curiosity rover first caught a faint trace of it in 2013, a blip so unexpected that researchers double-checked the data for errors. But the spikes kept returning, sometimes 10 times stronger than the background level, lingering for weeks before vanishing again. On Earth, 95% of methane comes from living organisms, from microbes to cows. So when Curiosity's laser spectrometer sniffed those fleeting bursts, the question became unavoidable. Was this the first whisper of life beyond our planet? The hunt for answers turned into a scientific tug-of-war. Some argued that methane could be produced by sterile chemistry water reacting with certain rocks or ancient gas seeping up from underground. But the pattern defied easy explanation. Unlike the steady trickle you'd expect from geological processes, these were sudden plumes, concentrated and sporadic, as if something were actively releasing them. Then in 2019, Curiosity hit the jackpot. A methane spike 21 parts per billion, the highest ever recorded. The timing was uncanny. It happened just as the European Space Agency's Trace gas orbiter passed overhead, offering a rare chance to cross-check the data from orbit. But when the orbiter looked down, it saw nothing. The methane had disappeared without a trace. This disconnect only deepened the mystery. Was Curiosity parked over some localized vent, a tiny methane geyser invisible from space? Or was the rover itself somehow producing false positives, its instruments reacting to Martian soil in ways no one anticipated? The debate raged on, with each new theory more inventive than the last. Some suggested ultraviolet light breaking down organic meteorite dust on the surface, while others proposed that methane might get trapped underground in icy cages called clathrates, releasing in unpredictable bursts. What makes these methane spikes so electrifying isn't just the possibility of life, it's how they expose the gaps in our understanding of Mars as a system. Even if the source turns out to be geological, the processes at work would still be alien to anything on Earth, reshaping our view of how planets evolve. And if by some cosmic stroke of luck the methane does trace back to microbes, that would mean life isn't a fluke confined to our blue marble, but a phenomenon woven into the fabric of the universe itself. Until we drill deeper or send sharper sensors, the red planet will keep its secrets, teasing us with clues that are just out of reach. The frustration is palpable among researchers. Every new detection feels like grabbing at smoke. But that's the thrill of science at the frontier. Sometimes the most profound discoveries begin not with a eureka, a moment, but with a stubborn anomaly that refuses to go away. And Mars, with its enigmatic puffs of gas, has given us precisely that, a riddle wrapped in a haze, waiting for the next chapter of exploration to unfold. For decades, fast radio bursts were the universe's ultimate disappearing act. Blink, and you miss them. Blasts of energy so brief they lasted mere milliseconds, yet so powerful they outshone entire galaxies. Astronomers assumed these were cosmic catastrophes, the final screams of collapsing neutron stars or black holes shredding their neighbors, one-off events violent and terminal. That certainty shattered in 2016 when researchers pointed the Arecibo telescope toward a galaxy 3 billion light-years away and caught something impossible, a fast radio burst repeating itself. Not just once, but multiple times in irregular bursts that defied every model. Suddenly, the leading theories collapsed. You can't have a second explosion from a star that's already destroyed itself. The repeater, dubbed FRB 1211-2, forced scientists back to the drawing board, spawning wild new hypotheses. Maybe magnetars, neutron stars with magnetic fields 1 trillion times stronger than Earth's, were cracking under pressure like cosmic fault lines. Or perhaps some exotic form of stellar collision left behind a lingering engine, pulsing like a lighthouse across the cosmos. Then entered CHIME, Canada's revolutionary radio telescope in British Columbia. Unlike traditional dishes, this sprawling array of metal cylinders scans the entire northern sky daily, catching whispers from the universe's noisiest corners. In just its first year of operation, CHIME detected hundreds of new FRBs, including dozens of repeaters, revealing patterns no one anticipated. Some burst in predictable cycles, flaring up every 16 days like clockwork. Others spat out weaker aftershocks between larger eruptions, hinting at systems far more complex than imagined. The most unsettling discovery: repeaters and one-off bursts behave differently. Repeaters tend to flicker at lower frequencies, as if their signals are wading through thicker cosmic static, while single bursts slice through cleaner and brighter. This split suggests multiple origins, some FRBs born in apocalyptic instants, others from objects that somehow survived their own fury. CHIME data became a goldmine, but with each answer came deeper questions. What could possibly reboot itself to blast out identical radio waves across billions of years? And why do some seem to cluster in specific regions of space, as if the universe has hotspots for these enigmas? What makes FRBs so thrilling isn't just their mystery, it's how they've humbled us. In less than a decade, we've gone from seeing them as cosmic fireworks to recognizing them as potential tools. Some researchers propose using FRBs as intergalactic yardsticks, their distorted frequencies revealing hidden matter between galaxies. Others dream of decoding their structures for signs of artificial origin, though no evidence supports that leap. For now, these bursts remain a tantalizing puzzle, proof that even the faintest whispers from the dark can rewrite our understanding of reality. Every new repeater CHIME finds is another piece of the mosaic, another clue in a detective story spanning the entire cosmos. And the best part, we're just learning how to listen. Venus has always been Earth's evil twin, a scorching, acidic hellscape with clouds of sulfuric acid and surface temperatures hot enough to melt lead. But in 2020, this planetary nightmare dropped a bombshell. Traces of phosphine gas floating high in its atmosphere. On Earth, phosphine is almost exclusively a byproduct of life, produced by microbes in oxygen-free environments like swamps and animal guts. So when astronomers at Cardiff University spotted its spectral fingerprint in Venus's clouds, the implications were staggering. Could there be life somehow surviving in those toxic shrouds 50 kilometers above the planet's surface? The discovery sent shockwaves through the scientific community. The team, led by Jane Greaves, had meticulously ruled out known abiotic processes, volcanoes, lightning, even meteorite dust, but nothing could explain the concentration they detected. Phosphine shouldn't last long in Venus's atmosphere. Ultraviolet radiation should break it apart within hours. Yet there it was, a persistent whisper that defied chemistry as we knew it. The paper, published in Nature Astronomy, ignited a firestorm. critics pounced, pointing to potential flaws in the data processing, had the signal been noise masquerading as science. Another team reanalyzing the same observations claimed they couldn't reproduce the results, arguing the phosphine might have been sulfur dioxide misread in the noise. But the controversy only deepened when independent groups found their own hints of phosphine. The Japanese Akatsuki orbiter, designed to study Venus's atmosphere, spotted anomalies consistent with the gas, though not conclusively. Suddenly, the debate wasn't just about one dataset, it was about how science reckons with anomalies that challenge our assumptions. The idea of airborne microbes in Venus's temperate cloud layers, floating like extremophiles in a cosmic petri dish, wasn't entirely far-fetched. Earth has life thriving in equally hostile niches, from acidic hot springs to the upper atmosphere. The backlash was fierce, though. Skeptics argued that exotic chemistry, not biology, must be at play. Perhaps unknown reactions between Venus's sulfur-rich atmosphere and its surface minerals. Others suggested high-altitude winds might concentrate trace gases in ways we don't yet understand. Amid the fray, NASA and ESA fast-tracked new missions to settle the debate. Veritas and Da Vinci Plus, set to launch in the late 2020s, will map Venus's geology and sample its atmosphere directly, hunting for phosphine and other biosignatures. Even private initiatives join the race, with Rocket Lab planning a dedicated probe to scan the clouds. What makes the phosphine saga so gripping isn't just the "could it be life?" question, it's how it exposes the messy, thrilling process of discovery itself. Here was a claim so extraordinary it demanded extraordinary evidence, and the scientific machine roared to life, dissecting every pixel of data. Whether Venus's phosphine turns out to be a sign of life, a fluke of chemistry, or something entirely new, it's already done its job, reminding us that the universe doesn't care about our expectations. Sometimes the most toxic places hide the most tantalizing secrets, and sometimes it takes a little controversy to push us closer to the truth. Physics thrives on precision, but what happens when two of our most trusted methods for measuring the universe's expansion start giving wildly different answers? That's the heart of the Hubble tension crisis, a problem so profound it's shaking cosmology to its core. On one side, we have the cosmic microwave background, the afterglow of the Big Bang, meticulously mapped by missions like Planck. Its data suggests the universe is expanding at about 67 kilometers per second per megaparsec. But then look at modern stars and supernova. Their brightness and redshift point to a rate closer to 73. That gap might seem small, but statistically, it's a chasm. These aren't measurement errors, they're fundamentally incompatible results, and the implications could rewrite our understanding of reality. The strangest part, both methods are rock solid in their own right. The cosmic microwave background approach is like reading the universe's birth certificate, tracing expansion from the very first moments. Meanwhile, the supernova method acts as a cosmic speedometer, tracking how fast galaxies are racing apart right now. They should agree, unless something's missing from our models. This discrepancy has physicists whispering about new physics, possibilities so radical they'd make Einstein pause. Maybe dark energy isn't constant but evolves over time, its push growing stronger as the cosmos ages. Or perhaps dark matter interacts with itself in ways we haven't accounted for, subtly altering the cosmic landscape. Some even speculate about extra dimensions warping gravity on vast scales, or that our corner of the universe sits inside a bizarre low-density bubble, skewing local measurements. The stakes couldn't be higher. In 2011, the team behind the supernova measurements won a Nobel Prize for proving the universe's expansion is accelerating. Now, their very data is hinting that our cosmic rulebook might need revisions. Telescopes like JWST are diving into the fray, scrutinizing Cepheid variable stars, cosmic yardsticks used to calibrate distances, to see if systematic errors lurk in the observations. But with early JWST data only deepening the mystery, confidence is growing that this isn't a glitch. It's a feature of the universe we've yet to understand. What makes the Hubble tension so electrifying isn't just the numbers, it's how it exposes science at its most alive. Here's a field willing to question its foundations, to entertain ideas that would have been heresy a decade ago. Whether the solution comes from tweaking gravity, reimagining dark energy, or something no one's dreamed up yet, one thing's certain: the cosmos is playing hardball. And every conflicting data point is another clue that we're on the verge of something monumental, a leap not just in what we know, but in how we see the fabric of reality itself. Black holes weren't supposed to get this big, at least, not the ones born from dying stars. That was the unshakable rule until 2019, when astronomers in China pointed their telescopes toward a cosmic heavyweight named LB1 and realized the rulebook needed burning. This monster, lurking 15,000 light-years away in our own galaxy, weighed in at a staggering 70 times the mass of the Sun, nearly double what theorists thought was possible for a black hole formed from a single collapsing star. The discovery sent shockwaves through astrophysics. Stellar evolution models had long held that massive stars nearing death would shed so much material through winds and eruptions that their cores couldn't collapse into black holes much heavier than 40 solar masses. Yet LB1 defied those calculations with brute force. Suddenly, researchers faced a glaring gap in their understanding. How did this gravitational titan come to exist? Some proposed it might be a primordial black hole, a relic from the universe's chaotic first moments when density fluctuations could have birthed black holes directly, bypassing stellar death altogether. Others suggested a dramatic merger history. Perhaps two smaller black holes had collided in a dense star cluster, their combined mass creating this behemoth. But even that theory had holes. Mergers typically kick the resulting black hole out of its birthplace at high speed, yet LB1 sat quietly in orbit with a companion star, showing no signs of a violent past. Then came the curveball. Follow-up observations hinted that LB1 might not be a black hole at all, but a stripped-down star called a blue lurker, masquerading as something darker. The debate grew heated, with teams reanalyzing the data, searching for subtle spectral clues that could settle the identity crisis. What emerged was a humbling lesson. Even our best tools can deceive us when probing the extremes of cosmic behavior. Whether LB1 is a record-breaking black hole or a stellar imposter, its existence, or even the illusion of it, has already reshaped astronomy. It forced scientists to revisit decades-old assumptions about how stars live, die, and leave behind remnants. Some now suspect entire populations of overweight black holes could be hiding in plain sight, overlooked because we didn't think to look for them. Others whisper about exotic physics, like hypothetical dark stars powered by annihilation rather than fusion. What makes LB1 so electrifying isn't just the mystery of its origin. It's the reminder that nature doesn't care about our models. Every time we think we've mapped the boundaries of the possible, the universe laughs and throws another impossibility our way. And in that uncertainty lies the thrill of discovery, the chance to peel back another layer of the cosmic unknown. The moon has always been seen as a dry, dusty wasteland, until radar waves pierced its polar regions in 2020 and bounced back with a story no one expected. Scientists analyzing data from NAS, a lunar reconnaissance orbiter, found reflections so bright and clear they could only mean one thing: liquid water. Not just trace amounts locked in ice, but sprawling reservoirs buried beneath the surface, hidden in shadowed craters where temperatures never rise above -170 degrees Celsius. The discovery sent shockwaves through planetary science. If true, these underground lakes could revolutionize space exploration, providing drinking water, oxygen, and even rocket fuel for future moon bases. But then came the twist. Another team re-examined the data and proposed that what looked like water might actually be frozen lunar dirt. The debate hinges on something called the dielectric constant, a measure of how materials respond to radar. Pure water ice and liquid water both reflect radar strongly, but so can certain types of dry, porous regolith. Researchers from the University of California argued that the signal patterns matched not liquid, but a specific kind of iron-rich clay formed by ancient volcanic activity. The moon's soil, they claimed, could be mimicking water's radar signature with nothing more than its mineral composition. Suddenly, the lakes were in doubt, and the scientific community split into camps. Some pointed out that even if the reflections came from clay, they were still concentrated in areas where water should theoretically accumulate, permanently shadowed regions acting as cold traps for volatile molecules. Others countered that without direct sampling, no interpretation could be definitive. What makes this mystery so pivotal isn't just academic, it's practical. Water on the moon isn't just a curiosity, it's a game changer for human expansion into space. Every liter of water mined locally saves NASA a roughly $20,000 in launch costs, the price of ferrying it from Earth. If the polar deposits are accessible, they could sustain lunar colonies and serve as pit stops for missions to Mars. But if it's just dry clay, stationing crews near the poles becomes far more complicated. That's why space agencies aren't waiting for consensus. NASA's upcoming Viper rover will drill into the lunar South Pole in 2024, hunting for ice with a 1-meter drill and spectrometer. Meanwhile, private ventures like SpaceX and Blue Origin are drawing up plans for ice mining operations, betting that the water is real. The irony is delicious. A discovery that could define the next era of spaceflight hinges on something as mundane as dirt. Yet that's the beauty of exploration. Sometimes the biggest questions have the simplest answers, hiding in plain sight until we look closely enough. Whether the moon's poles hold lakes or just clever geology, the search itself is reshaping how we see our nearest celestial neighbor. And one way or another, we're about to learn just how generous or miserly the moon really is. For nearly a century, scientists had theorized that the universe wasn't just a random scattering of galaxies. It had a hidden architecture, a vast cosmic web woven from threads of dark matter. But proving it required seeing the unseeable. Then in 2021, astronomers pulled off the impossible. They took the first direct snapshot of this intergalactic skeleton, and what they found was more breathtaking than anyone had dared to predict. The breakthrough came from an ingenious trick using quasars, the dazzling cores of distant galaxies powered by supermassive black holes as backlights. As their light traveled billions of years to reach Earth, it passed through the faint hydrogen gas clinging to the web's filaments. Like sunlight filtering through stained glass, the quasar's beams left spectral fingerprints, revealing where these ghostly threads crisscrossed the cosmos. The resulting map was staggering, a three-dimensional tapestry of glowing tendrils connecting galaxies across 11 billion light-years, precisely where dark matter models said they should be. This wasn't just a pretty picture, it was a triumph of cosmological detective work. For decades, simulations had suggested that dark matter's gravity sculpted the universe into this filamentary structure, with galaxies clustering at the intersections like pearls on a string. But without observational proof, it remained speculative. The cosmic web's debut changed everything. The filaments matched simulations down to their temperature, density, and distribution, confirming that dark matter isn't just a placeholder in equations, it's the invisible scaffolding holding reality together. What makes this discovery so revolutionary isn't just the validation of dark matter. It's how it reshaped our understanding of the universe's growth. Those filaments aren't passive roadmaps, they're highways funneling gas into galaxies, fueling star births and black hole feasts. They're the reason galaxies spin where they do, why clusters collide along predictable paths, and perhaps even how life found the raw materials to emerge. The cosmic web isn't just structure, it's the universe's circulatory system, and we're finally learning to trace its veins. Yet for all its clarity, the map raised new mysteries. Some filaments were denser than models predicted, as if dark matter clumped in ways we don't yet understand. Others stretched farther than expected, hinting at larger-scale patterns still uncharted. And lurking in the data were whispers of even older webs, structures that might have formed before galaxies even existed. It's a reminder that every cosmic milestone comes with fresh questions, and that the universe's greatest revelations often start with learning just how much we've been missing. In late 2019, skywatchers noticed something unsettling. One of the night sky's brightest stars, Betelgeuse, was fading fast. This wasn't some subtle dip. The red supergiant, a familiar shoulder in Orion's constellation, lost over 2/3 of its brilliance in just months. Panic rippled through astronomy circles. Betelgeuse was a ticking time bomb, a star already on the brink of collapsing into a supernova. Could this dimming be the final countdown? Social media lit up with doomsday speculation, while researchers scrambled for telescopes to witness what might have been the precursor to the most spectacular stellar explosion in recorded history. Then came the twist. Betelgeuse wasn't dying, it was just sneezing. Hubble's ultraviolet eyes caught the culprit, a colossal belch of superheated plasma and dust. The star had ejected a cloud of material so vast it briefly obscured its own light, like a cosmic lamp shrouded in smoke. Spectrographic analysis revealed the dust wasn't even exotic, mostly silicon and aluminum oxides, the same stuff that makes up earthly sand and sapphires. But the scale was mind-bending. This wasn't a gentle puff. Betelgeuse had hurled a chunk of its outer layers weighing several times our moon's mass into space, cooling into an opaque veil that drifted across our line of sight. What made the great dimming so fascinating wasn't just the false alarm. It was the window it opened into how massive stars behave as they near their violent ends. Betelgeuse is an erratic old giant, its surface bubbling with convection cells larger than our solar system. These stars don't fade quietly, they convulse, shedding material in fits and starts. Some astronomers now think the dimming might have been part of a cycle, with historical records hinting at similar events in the 1800s and 1930s. Others speculate it could signal a more dramatic transformation. Perhaps Betelgeuse is quietly transitioning from burning helium to carbon in its core, a signpost on the road to eventual collapse. The real lesson here: space keeps us humble. Even a star we've studied for centuries can still catch us off guard, blurring the line between routine stellar drama and genuine catastrophe. And while Betelgeuse's fireworks were postponed, they're not cancelled. One day, whether next year or in 100 millennia, that dimming will be real, and when it happens, the show will outshine every other star in our sky combined. Until then, we'll keep watching, reminded that even the familiar can hide the extraordinary. The Milky Way should be drowning in tiny galaxies. At least, that's what our best simulations of dark matter insisted. According to the math, our galaxy's gravitational pull ought to have snagged hundreds of dwarf satellite galaxies, each a faint smudge of stars orbiting like fireflies around a street lamp. But when astronomers started counting, the numbers didn't add up. Where theory predicted a bustling cosmic entourage, reality showed only a handful. This glaring mismatch, dubbed the missing satellites problem, became one of the most stubborn puzzles in modern astrophysics and a crack in our understanding of dark matter itself. The roots of the mystery trace back to the 1990s, when supercomputer models first mapped how dark matter should clump together in the early universe. These simulations painted a vivid picture, vast halos of invisible material, each acting as a gravitational seed for galaxies. The bigger halos birthed giants like the Milky Way, while smaller ones formed dwarfs, dim, star-sparse companions. But as telescopes grew sharper, the expected swarm of satellites failed to materialize. Instead of hundreds, we've confirmed barely 60, most so faint they blur into the background like cosmic ghosts. For years, scientists scrambled to explain the gap. Maybe dwarf galaxies were just too dim to spot, their stars scattered too thinly against the blackness. Yet even as instruments like the Sloan Digital Sky Survey peeled back the veil, the numbers stayed stubbornly low. Others wondered if something was suppressing star formation in these satellites, leaving them dark and nearly invisible. But the most provocative explanation struck at the heart of cosmology itself. What if dark matter doesn't behave the way we think? The standard model assumes dark matter is cold, slow-moving particles that clump easily, creating the dense halos predicted by simulations. But if dark matter is slightly warmer, with particles zipping around faster, they'd resist clustering into tiny halos, leaving fewer dwarfs. Alternative theories like fuzzy dark matter or self-interacting dark matter gained traction, each tweaking the rules just enough to match observations. It's a high-stakes game of cosmic whack-a-mole. Every solution solves one problem but risks creating another elsewhere in the model. What makes the missing satellites problem so electrifying isn't just the scientific tug of war, it's what it reveals about the messy process of discovery. Here's a case where reality refused to conform to elegant theory, forcing astronomers to question their deepest assumptions. And while recent discoveries of ultra-faint dwarfs, some with as few as 100 stars, have narrowed the gap, the tension lingers. Every new dwarf found is a clue, a piece of the puzzle that might someday force us to rewrite the rules of the cosmos. The irony is delicious. The very stuff that makes up 85% of the universe's matter remains hidden, its nature inferred only through its gravitational fingerprints. And in the quiet absence of those missing satellites, dark matter whispers its loudest challenge, yet not just to our telescopes, but to our imagination. How many more cosmic secrets are lurking just beyond the edge of our vision, waiting for the right light to reveal them? When the James Webb Space Telescope unveiled its first deep-field images in 2022, astronomers expected to see the universe's infancy, faint, fledgling galaxies blinking into existence. Instead, they stared at cosmic toddlers that had no business being so grown up. There, glowing in the infrared haze, were massive, fully formed galaxies dating back just 300 million years after the Big Bang. These weren't the scrappy proto-galaxies theorists had predicted. They were sprawling cities of stars, hundreds of billions of solar masses strong, looking as polished as galaxies 10 times their age. The discovery sent shockwaves through cosmology, forcing scientists to confront an uncomfortable truth. Our models of cosmic evolution might be missing something fundamental. The problem isn't just that these galaxies exist, it's that they're too good at existing. Modern simulations, which factor in the slow dance of dark matter and gas, suggest it should have taken at least 500 million years for gravity to sculpt such behemoths. Yet JWST infrared eyes revealed structures with intricate spiral arms, dense bulges, and even evidence of supermassive black holes, all crammed into a sliver of cosmic time. It's like finding a skyscraper in the middle of the Stone Age. Some researchers scrambled to tweak their models, proposing that star formation in the early universe might have been wildly more efficient than we thought, with gas collapsing into stars at nearly 100% efficiency. Others wondered if dark matter behaved differently in those primordial eras, clumping faster and giving galaxies a head start. But the most radical idea, that the Big Bang might not mark the true beginning of time, that some form of pre-Big Bang activity could have seeded these galactic giants before the clock even started ticking. What makes this discovery so disorienting isn't just the scale of the anomaly, it's how little wiggle room it leaves. JWST data is pristine, and the galaxy's redshifts place them squarely in that impossibly early epoch. There's no convenient loophole, no calibration error to blame. Either we've misunderstood how quickly galaxies can assemble, or we've misjudged the universe's birth certificate. And with each new JWST observation, the puzzle grows richer. Some of these ancient galaxies show shockingly low levels of heavy elements, as if they formed from nearly pure hydrogen, while others are already dust-choked, hinting at generations of stars that lived and died in the blink of a cosmic eye. The implications ripple far beyond astronomy textbooks. If galaxies can mature this quickly, it reshapes our search for life's origins. A faster timeline means habitable planets might have emerged billions of years earlier than presumed, stretching the window for intelligence to arise. It also forces us to reconsider how rare or common advanced civilizations might be across deep time. But perhaps the most humbling lesson is how much we still don't know about the universe's opening act. For all our telescopes and supercomputers, the cosmos keeps revealing layers of complexity we never dreamed to model. JWST impossible galaxies aren't just outliers, they're signposts pointing to a new frontier where the rules of cosmic dawn might be waiting to be rewritten. In 2019, astronomers scanning the sky with Australia's ASCAP radio telescope stumbled upon something that defied all expectations: massive, ghostly rings of radio emission, each spanning hundreds of thousands of light years, dwarfing the galaxies at their centers. They called them odd radio circles, or ORC, but their true nature remains one of the most baffling cosmic puzzles of the decade. At first glance, these ORCs resemble ripples from a stone tossed into a pond, except the pond is intergalactic space and the stone is something we've yet to identify. The circles are invisible in optical, infrared, and X-ray light, revealing themselves only in the radio spectrum. Their symmetry is uncanny, as if sculpted by some unseen hand, and they're not drifting. They're anchored to galaxies, hovering like cosmic halos with no clear explanation. The Discovery team, led by astrophysicist Ray Norris, nicknamed the first one Dragonfly for its ethereal, wing-like loops, but this was no delicate insect. These structures pack enough energy to outshine entire galaxies, and yet they leave no trace of what birthed them. Theories erupted like sparks from a fire. Could they be shock waves from cataclysmic events, like supermassive black hole mergers or galaxy-scale supernova? Maybe, but no known explosion could produce rings so vast or symmetrical. Others suggested a more exotic origin, the aftermath of a gargantuan jet blasted by a quasar, its plasma bubbles inflated over eons. Yet when astronomers examined the galaxies at the ORC's hearts, they found no signs of such violent activity. Then came the wild card wormholes. Some theorists proposed that these rings might be the mouths of Einstein-Rosen bridges, their gravitational lensing warping radio waves into circular mirages. It's a stretch, but in the absence of mundane explanations, even radical ideas get a seat at the table. The plot thickened when follow-up observations revealed ORCs aren't just rare flukes. ASCAP and other telescopes have since spotted dozens more, suggesting these phenomena might be common. We just hadn't noticed them until now. Some ORCs even appear to encircle multiple galaxies, their overlapping rings hinting at interactions between galactic neighbors. But the real twist, a few of these circles seem to be growing, expanding over mere decades, a blink of an eye in cosmic terms. Whatever's driving them isn't just powerful, it's active right now, reshaping the fabric of space around it. What makes ORCs so thrilling isn't just their mystery, it's how they expose the limits of our cosmic vision. Here were structures so enormous they'd been hiding in plain sight, overlooked because no one thought to look for something so bizarre. They're a reminder that the universe still holds surprises on scales we're only beginning to map, and that sometimes the most profound discoveries start with a simple question: what is that? Until we train sharper eyes on these enigmatic rings, they'll remain celestial Rorschach tests, each interpretation revealing as much about our imagination as about the cosmos itself. The Milky Way has always been our galactic home, a familiar spiral of starlight stretching across the night sky. But in 2010, scientists staring at data from NASA's Fermi Gamma-Ray Space Telescope got the astronomical equivalent of finding secret rooms in your basement. Stretching 25,000 light-years above and below the galactic plane, two colossal bubbles of scorching hot gas were billowing outward, pumping out enough gamma radiation to light up half the visible universe. Dubbed the Fermi bubbles, these structures had been hiding in plain sight, masked by the galaxy's glow until Fermi's sharp gamma-ray vision peeled back the curtain. What made this discovery so electrifying wasn't just the bubble's size, though at 50,000 light-years tall, they dwarf almost every other structure in the Milky Way but their energy. The gamma rays weren't the faint whispers of ancient events. They were screams signaling particles moving near the speed of light. That kind of violence doesn't happen without a cosmic cataclysm. The immediate suspect, our galaxy's supermassive black hole, Sagittarius A star. Astronomers theorized that millions of years ago, it might have gorged on an enormous gas cloud or even a wayward star cluster, triggering twin jets of plasma that punched through the galactic disk like geysers. These jets, now cooled into bubbles, would be the aftermath, a fossil record of the black hole's last big meal. But not everyone bought the black hole feast theory. Some researchers pointed out that the bubble's edges were too sharp, their structure too symmetrical for a chaotic eruption. Others noted that the gamma rays weren't distributed evenly. They clustered in strange filaments and knots, as if the bubbles were threaded with invisible cosmic wires. Alternative explanations bloomed like supernova. Maybe the bubbles were relics of a burst of star formation so intense it sent shockwaves rippling through the galaxy's halo. Or perhaps dark matter annihilations, theoretical collisions between invisible particles, were generating the gamma rays as a byproduct, the wildest idea. That we were seeing the Milky Way's version of a particle accelerator, where magnetic fields far beyond anything on Earth were slinging protons and electrons to unimaginable energies. The debate grew even fiercer when follow-up observations revealed a second, fainter set of bubbles nested inside the first, like Russian dolls of high-energy physics. X-ray telescopes spotted their outlines while radio arrays mapped their magnetic skeletons. Each new dataset added pieces to the puzzle, but the full picture remained frustratingly unclear. Even the bubble's age became a point of contention. Estimates ranged from 2 million to 10 million years old, depending on whether you trusted stellar motions or plasma simulations. What makes the Fermi bubbles more than just a scientific curiosity is what they represent, a glimpse into the Milky Way's volatile past. If the black hole theory holds, they're proof that Sagittarius A star isn't always the quiet neighbor we see today. It has a temper capable of eruptions that reshape the galaxy. If the star formation or dark matter ideas pan out, they reveal entirely new ways for galaxies to channel energy across cosmic scales. And if the truth lies somewhere beyond our current theories, well, that's the most exciting possibility of all. Because the Fermi bubbles aren't just structures, they're a challenge, a reminder that even our home galaxy still has stories left to tell. Every gamma-ray photon we detect is another sentence in a saga we're only beginning to read. Tabby's star refuses to give up its secrets easily, just when astronomers thought they'd cracked the case, dismissing the alien megastructure hype in favor of dust clouds. New observations in 2023 threw another curveball. High-resolution data from the James Webb Space Telescope revealed the dust isn't behaving like ordinary interstellar debris. Instead of drifting in a uniform haze, it's clumped in bizarre, lopsided formations as if something or someone is stirring the pot. For years, the leading theory had been mundane but elegant. Swarms of cold, micron-sized dust grains orbiting the star were blotting its light unevenly. But JWST infrared eyes spotted something stranger. The dust isn't just patchy, it's dynamic, with some particles radiating heat at temperatures far higher than expected for simple cosmic soot. These aren't the lazy, frozen motes we see floating between stars. They're active, almost restless, as if caught in some unseen turbulence. Even more perplexing, the dimming events don't align with any predictable orbital patterns. Instead of repeating at regular intervals, they flare up erratically like a malfunctioning stage light. The dust's composition deepened the riddle. Spectra showed traces of silica and graphite, materials you'd expect from pulverized asteroids or vaporized comets, except there's no clear source for such devastation. No planetary wreckage circles close enough to explain the sheer volume of debris, and no nearby objects show signs of recent collisions. One provocative study suggested the dust might be self-lensing, dense knots warping the star's own light as they pass in front, a phenomenon never observed around other stars. What makes this update so tantalizing isn't just the data, it's how it exposes the limits of our cosmic detective work. We've ruled out megastructures, but what's left defies easy categorization. Could an unseen planet with wild orbital swings be shepherding this dust into odd configurations? Or is Tabby's star harboring some exotic form of stellar activity we've never witnessed before? The truth, as always, lies somewhere between the known and the unimaginable. Every time we think we've pinned this star down, it wriggles free, leaving us with more questions than answers, and proving once again that the universe's greatest trick is keeping us guessing. The outer solar system holds a secret so massive it could rewrite our cosmic family tree, a hidden giant lurking in the darkness beyond Neptune, tugging at smaller objects with gravitational whispers. Since 2014, astronomers tracking icy bodies in the Kuiper belt noticed something eerie. Clusters of these distant objects shared bizarrely similar orbits, tilted at angles that shouldn't happen by chance alone. Their paths aligned as if sculpted by an unseen hand, something far larger than Pluto, perhaps 10 times Earth's mass, looming in the frozen outskirts of our star's domain. This phantom, dubbed Planet 9, isn't just a hunch. The math insists something's out there. The evidence hinges on 6 extreme trans-Neptunian objects whose elongated orbits point like compass needles toward the same patch of sky. Statistically, the odds of this alignment occurring naturally are less than 1 in 10,000. Caltech researchers Konstantin Batygin and Mike Brown, who first pieced together the pattern, compare it to finding 6 clocks in a room all frozen at the exact same time. Coincidence stretches only so far before physics demands an explanation. Their models suggest a distant super-Earth, tracing a looping path so vast it takes 10 to 20,000 years to complete a single orbit around the Sun. At its farthest, it would dwell 20 times farther out than Neptune, so remote that reflecting sunlight would make it nearly invisible to our telescopes. Yet Planet 9 isn't the only suspect in this cosmic whodunit. Some theorists propose an even stranger culprit, a primordial black hole no larger than a grapefruit, left over from the universe's explosive birth. Though tiny, such an object would pack 5 to 10 Earth masses, yanking Kuiper belt objects with comparable force. The difference, instead of reflecting light, it would swallow it whole, explaining why surveys like Pan-STARRS and DS haven't spotted a planet. Harvard astronomers have even outlined how to hunt this dark interloper, looking not for its silhouette, but for flares of gamma radiation as it annihilates nearby dark matter. The search has become a grand technological chess match. The Subaru telescope in Hawaii scans the predicted orbital arc, its hyper-subprime cam capable of spotting a faint dot moving against the starfield. Meanwhile, the Vera Rubin Observatory, set to come online in 2025, will image the entire southern sky every few nights, catching any slow-motion drift of a distant world. Even NASA's TESS mission, designed to hunt exoplanets, has joined the chase, repurposed to monitor the outer solar system for flickers of reflected light. What makes this hunt so electrifying isn't just the potential discovery, it's the high-stakes gamble of cosmic hide and seek. If Planet 9 is real, it's a time capsule from the solar system's violent youth, perhaps ejected during the gas giant's chaotic dance billions of years ago. If it's a black hole, it's a relic of the Big Bang itself, lurking unnoticed in our cosmic backyard. And if it's nothing, then those skewed Kuiper belt orbits become an even deeper mystery, hinting at flaws in our understanding of gravity itself. Every telescope trained on the outer dark is a bet against the unknown, a wager that the universe still has cards left to reveal. The irony is delicious. We've mapped galaxies billions of light years away, yet our own solar system might still hide a giant. Whether planet or black hole or something stranger, one thing's certain: the outer dark isn't empty. It's waiting, and with each new search, we inch closer to uncovering what's been pulling the strings all along. The cosmic microwave background should be a nearly perfect snapshot of the universe's infancy, a glow so uniform its temperature varies by less than 100,000th of a degree. But in 2005, astronomers analyzing data from NASA, a Wilkinson microwave anisotropy probe, stumbled upon a cosmic anomaly so chilling it earned the nickname the cold spot. Stretching over 1 billion light-years in the constellation Eridanus, this region of space isn't just slightly cooler, it's a freezing void, dipping 70 microkelvins below the surrounding temperature. That doesn't sound like much until you consider the scale. This isn't a local weather pattern, it's a gaping hole in the thermal fabric of the early universe. At first, scientists assumed it was a glitch, some artifact of instrument noise or foreground interference from our own galaxy. But as more telescopes turned their gaze toward the anomaly, including Europe's Planck satellite, the cold spot refused to vanish. Its edges were too sharp, its profile too distinct to dismiss as static. Theorists scrambled for explanations ranging from the mundane to the mind-bending. Maybe it was a supervoid, an underdense region of space where fewer galaxies meant less gravitational pull, stretching photons' wavelengths as they passed through, an effect known as the integrated Sachs-Wolf effect. Yet when teams mapped the area with optical telescopes, they found no void large enough to account for the temperature drop. The cold spot was real, and it was playing by no one's rules. That's when things got truly wild. Some cosmologists floated a hypothesis straight out of science fiction. The cold spot might be a bruise, a collision between our universe and a neighboring bubble universe during cosmic inflation, could have sapped energy from that patch of spacetime, leaving behind a telltale cold imprint. The math almost worked. Multiverse theories predict such collisions should create disk-like signatures in the CMB, and the cold spot's shape fits uncomfortably well. Other physicists bristled at the idea, calling it a Hail Mary pass to salvage untestable theories. They countered with alternatives, perhaps an ancient cosmic texture defect, a knotted flaw in spacetime's structure from the universe's first moments, had unwound there, releasing energy in a way that left the region colder. Or maybe we're seeing the shadow of a gargantuan black hole's gravity well from a previous eon, a relic of a cyclical universe, the most unsettling possibility. That the cold spot isn't physics breaking down, it's statistics. When you map the entire sky, random fluctuations should occasionally produce rare cold patches purely by chance. The problem is, simulations show something this extreme should occur only once in every 50 universes. Are we the lucky lottery winners of cosmic noise, or is the universe trying to tell us something? The debate rages on, with newer analyses from the Atacama Cosmology Telescope adding fuel to the fire. Their ultra-precise maps confirm the spot's existence but can't pin down its origin. What makes the cold spot so unnerving isn't just its existence, it's what it represents. A crack in our otherwise pristine model of cosmic dawn, a place where the universe's baby photos don't match the predictions. Whether it's a multiverse bruise, a phantom void, or just a statistical fluke, it's a reminder that even our best theories are provisional. The cosmos keeps a few cards close to its chest, and the cold spot might be the ultimate poker face, a cosmic riddle written in degrees above absolute zero, waiting for someone to decode its frosty secrets. The universe was supposed to slow down. That's what every physicist believed until 1998, when two separate teams of astronomers made a discovery so shocking it turned cosmology upside down. By studying distant supernova exploding stars so bright they can outshine entire galaxies, researchers expected to measure how much the universe's expansion was gradually breaking under gravity's pull. Instead, their telescopes revealed something impossible. The universe wasn't slowing at all. It was speeding up, as if some invisible hand had pressed the cosmic gas pedal. The implications were staggering. Either Einstein's theory of gravity was wrong, or a mysterious force was fighting back against the collapse of everything. They called it dark energy, and it would soon become the greatest unsolved puzzle in physics. The evidence came from Type Ia supernova, nature's most precise cosmic yardsticks. These stellar explosions always flare with the same intrinsic brightness, making them perfect for measuring distances. By comparing how dim they appeared with how far away they were, scientists could trace the universe's expansion rate over billions of years. The teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, expected to find that ancient supernovae were brighter than predicted, indicating the universe expanded faster in the past and had since slowed. Instead, the opposite was true. The most distant supernovae were dimmer than they should have been, meaning space was stretching faster now than it had billions of years ago. The results were so counterintuitive that both teams spent years double-checking for errors, ruling out dust, supernova variations, even faulty instruments. The data held firm. The universe wasn't just expanding, it was accelerating as if repelled by some unseen anti-gravity. The culprit, dark energy, a placeholder name for whatever was causing this runaway expansion. Calculations showed it made up a jaw-dropping 68% of the universe's total energy density, dwarfing both ordinary matter and dark matter. Yet its nature remained and still remains a mystery. The simplest explanation, Einstein's infamous cosmological constant, a term he'd once added to his equations to keep the universe static, later calling it his greatest blunder. Revived for a new era, it represented the energy of empty space itself, a constant push embedded in the fabric of reality. But there was a problem. Quantum field theory predicted the cosmological constant should be 120 orders of magnitude stronger than observed. This wasn't just a gap in knowledge, it was the worst mismatch in science. Alternative theories exploded like the supernova that started it all. Maybe dark energy wasn't constant but evolved over time, a dynamic field dubbed quintessence. Or perhaps gravity itself behaved differently across cosmic distances, breaking down in ways Einstein never anticipated. The wildest idea that we were witnessing the early stirrings of a big rip, where dark energy's grip would eventually tear apart galaxies, stars, even atoms. What made the discovery so unsettling wasn't just the science, it was the philosophical quake it triggered. For centuries, humans had seen the universe as a clock winding down. Now we lived in a runaway train, hurtling toward an uncertain future driven by a force we couldn't see or explain. The 1998 papers won their authors the Nobel Prize, but the celebration was tinged with unease. Dark energy wasn't just another puzzle, it was a fundamental gap in our understanding of reality, one that might require rewriting physics itself. 25 years later, we're no closer to cracking it. New telescopes like Euclid and the Vera Rubin Observatory are mapping billions of galaxies to trace dark energy's fingerprints, while lab experiments hunt for exotic particles that might explain its pull. Yet for all our tools, the universe keeps its secrets, expanding faster with every passing moment, carrying us further into the unknown. The lesson: sometimes the biggest discoveries don't just answer questions, they reveal how much we've been missing all along. On a summer morning in 1908, a fireball streaked across the skies of Siberia with the force of 1,000 atomic bombs. Witnesses near the Podkamennaya Tunguska River described a blinding blue-white light, followed by a shockwave so powerful it knocked people off their feet hundreds of miles away. When scientists finally reached the remote site decades later, They found 800 square miles of forest flattened like matchsticks, trees scorched and uprooted in a radial pattern, their trunks pointing away from ground zero. Yet at the epicenter stood a grove of bizarrely intact trees, stripped of branches but still upright, as if something had detonated midair with unimaginable force. The Tunguska event remains the largest impact disaster in recorded history, yet its origin is a riddle wrapped in contradictions. No crater was ever found. No fragments of a meteorite or comet were recovered. Even the timing was peculiar. The explosion occurred around 7:17 in the morning local time, yet night skies across Europe glowed eerily for weeks afterward, bright enough to read newspapers at midnight. The leading theory, a cosmic intruder, perhaps 60 meters wide, vaporized 5 to 10 kilometers above the surface, releasing energy equivalent to 10 to 15 megatons of TNT. But was it a stony asteroid or an icy comet? The debate hinges on subtle forensic clues. Asteroid proponents point to the lack of water in atmospheric spectra recorded after the blast, suggesting a rocky body. But comets have their defenders too. The glowing nights resemble effects seen after the 1994 impact of comet Shoemaker-Levy 9 into Jupiter, where fine dust high in the atmosphere scattered sunlight globally. Then there's the strange behavior of the Tunguska object. Eyewitnesses reported it zigzagging across the sky, an observation modern models suggest could result from a comet's fragile nucleus breaking apart under atmospheric pressure, creating a chain of explosions. The most tantalizing clue: in 2013, researchers analyzing peat from the blast site found microscopic mineral spheres rich in iridium and other elements common in meteorites but arranged in ratios unlike any known asteroid. The absence of larger debris only deepens the enigma. Some speculate the object was a rare rubble pile asteroid, a loosely held together mass of gravel that disintegrated completely. Others propose an even wilder idea, a chunk of antimatter or a miniature black hole passing through Earth, though both theories strain credibility without physical evidence. The truth might lie in a middle ground, a carbonaceous asteroid packed with organic compounds that burned up too efficiently to leave traces. Or perhaps the answer is simpler: we've been looking in the wrong places. Recent expeditions to nearby Lake Chico, where sonar detected a dense, cone-shaped object buried under sediment, reignited hopes of finding fragments, until drilling confirmed it was just an ancient volcanic formation. What makes Tunguska so endlessly fascinating isn't just the scientific whodunit, it's the chilling precedent it sets. An explosion of that magnitude over a populated area today would level a major city with casualties in the millions. NASA now tracks over 30,000 near-Earth objects, yet estimates suggest we've spotted less than 40% of potential Tunguska-sized threats. The event isn't just a historical curiosity, it's a warning etched in scorched Siberian pines, proof that the universe doesn't care about our calendars or borders. Whether comet or asteroid, the Tunguska visitor left behind more than flattened trees. It left a question mark hanging over our heads, a reminder that the next cosmic surprise could arrive anytime from any direction. And this time, we might not be lucky enough for it to land in the middle of nowhere. The moon has never been known for its magnetic personality, literally. Today, it barely generates a field at all, just faint whispers compared to Earth's robust magnetic shield. But when Apollo astronauts brought back ancient moon rocks in the 1970s, those samples held a shocking secret. Locked inside their crystalline structures were traces of a magnetic field once as strong as Earth's, a revelation that left scientists stunned. How could a world with a core barely 1/4 the size of our planet's have sustained such a powerhouse dynamo for billions of years? The answer would rewrite everything we thought we knew about lunar history. At the heart of the mystery lies a process called a dynamo, the swirling, molten metal in a planet's core that generates magnetic fields like a cosmic generator. Earth's dynamo thrives thanks to its massive, churning outer core of liquid iron. But the Moon, its core is tiny and by all rights should have cooled and solidified eons ago, snuffing out any magnetic activity. Yet Apollo's rocks told a different story. Some bore magnetic imprints dating back 3.5 billion years, suggesting the Moon's field persisted for over 1 billion years after its formation. That's like finding a candle still burning long after its wax should have melted away. Theories erupted like moon volcanoes. Maybe the lunar core stayed molten longer than expected, kept alive by radioactive elements or tidal forces from a then closer Earth. Others proposed a radical mechanical dynamo, where the Moon's early, unstable rotation could have sloshed its core like a centrifuge, generating brief but intense fields. But the real breakthrough came from simulations in 2021. Researchers discovered that if the Moon's mantle, the layer above its core, was once hot enough to convect violently, it could have acted like a thermal blanket, trapping heat and keeping the core simmering far longer than models predicted. Picture a thermos bottle around the Moon's heart, preserving its magnetic vitality against the cold of space. The implications ripple far beyond lunar geology. If small bodies like the Moon can sustain magnetic fields, it raises tantalizing questions about other rocky worlds: Mercury, Mars, even exoplanets. Could some have hidden dynamos beneath their silent surfaces? And what does it mean for the search for life? Magnetic fields shield atmospheres from solar winds. A briefly magnetic Moon might have once cradled a thin, temporary atmosphere. The rocks Apollo brought home were more than souvenirs. They were time capsules, preserving the ghost of a lunar force field we never knew existed. Perhaps the most humbling lesson is how wrong we were. For decades, the Moon was the textbook example of a dead world. Its geologic clock stopped long ago. Now we know it had a vibrant, churning interior capable of feats we're only beginning to understand. Those silent gray plains, they're the scars of a world that was once alive with invisible energy, a reminder that even our closest cosmic neighbor still has secrets buried in its bones. In the silent darkness of the Antarctic ice, 2.5 kilometers below the surface, an array of sensors waited patiently for a ghost to pass through. On September 22, 2017, the IceCube Neutrino Observatory caught the unimaginable, a single, ultra-high-energy neutrino that had traveled 4 billion light-years across the cosmos before slamming into Earth. Unlike ordinary cosmic rays, this particle left no visible trail. It barely interacted with matter at all, but its energy screamed its origin. A blazar dubbed TXS0506+056, a supermassive black hole devouring its surroundings while firing twin jets of plasma straight at Earth. This wasn't just another cosmic detection, it was the Rosetta Stone of high-energy astrophysics, the first time humanity had traced a neutrino back to its violent birthplace beyond our galaxy. For decades, neutrinos had taunted scientists with their elusiveness. Trillions pass through your body every second without a trace, earning them the nickname ghost particles. They're born in the heart of nuclear reactions, whether in the sun's core, exploding stars, or the relativistic jets of black holes. Yet they rarely bump into atoms, making them nearly impossible to track. IceCube's genius was turning a cubic kilometer of Antarctic ice into a neutrino trap. When the occasional neutrino does collide with an atom, it creates a secondary particle called a muon that streaks through the ice faster than light can travel in that medium, producing a faint blue glow called Cherenkov radiation. Sensors buried in the ice capture that glow, mapping the neutrino's trajectory like cosmic fingerprints. The 2017 event, nicknamed IceCube 170922A, was no ordinary detection. Packing over 200 tera-electron-volts of energy, 40 times more than protons in the Large Hadron Collider, it carried the unmistakable signature of an extragalactic accelerator. Within moments of the alert, telescopes worldwide swiveled toward the blazar, catching it in the throes of a violent outburst. gamma rays, X-rays, and radio waves flooded in, painting a picture of a monster black hole shredding matter and hurling particles across the universe at nearly light speed. The correlation was undeniable. This distant leviathan had launched the neutrino like a cosmic bullet, and we'd caught it red-handed. The implications rewrote astrophysics overnight. For a century, the origins of ultra-high-energy cosmic rays had been one of the universe's best-kept secrets. These particles, mostly protons, strike Earth's atmosphere with energies 1,000,000 times greater than anything we can produce in labs. But their charged nature means magnetic fields scramble their paths, masking their birthplaces. Neutrinos, being neutral, fly straight, offering a direct line back to their sources. IceCube's Blazar link proved that active galaxies really are cosmic particle accelerators, capable of generating not just photons but the most energetic matter in existence. Yet the discovery raised as many questions as it answered. Why had this particular Blazar, one of thousands, produced such an unmistakable neutrino? Was its jet angle just right, or did some internal cataclysm, a star torn apart, perhaps supercharge its output? Even more puzzling, follow-up studies found that blazars like TXS 0506 plus 056 couldn't account for all high-energy neutrinos. The universe had to be hiding other sources, from colliding galaxy clusters to weird stellar remnants we've yet to imagine. What makes this breakthrough so transformative isn't just the science, it's the dawn of an entirely new way to see the cosmos. Neutrino astronomy joins light, gravitational waves, and cosmic rays as a fourth pillar of observation, revealing universes hidden from traditional telescopes. IceCube's successors, like the planned cubic kilometer neutrino telescope under the Mediterranean, will expand our ghost hunting nets, turning the Earth itself into a telescope for the invisible. Every neutrino captured is a message in a bottle from the universe's most extreme environments, and we're only just learning to read them. The Blazar's neutrino wasn't just a particle, it was a postcard from the edge of physics, stamped with the violent beauty of a black hole's fury. And it's only the first of many. The Milky Way stars have always been seen as silent sentinels, their light steady and unchanging across human history. But in 2022, the European Space Agency's Gaia spacecraft tore up that assumption with a revelation as subtle as it was seismic. Buried in its third data release, containing precision measurements of nearly 2 billion stars, was something no one expected. The faint, universal tremors of starquakes, tiny ripples pulsing across stellar surfaces like cosmic heartbeat echoes. These weren't just curiosities, they were time machines revealing hidden chapters of our galaxy's past written in the shudders of suns both living and dead. Gaia's original mission was astrometry, mapping star positions with unmatched precision. But its instruments proved sensitive enough to catch something far more dynamic: the rhythmic expansion and contraction of stars' outer layers, oscillations so slight they shift a star's brightness by mere fractions of a percent. Like listening to a symphony's vibrations to reconstruct its instruments, astronomers realized these quakes could unveil stellar interiors with startling clarity. Young, burning stars throbbed with predictable rhythms, but the real shock came from Gaia's dead targets, white dwarfs, the dense embers of long-dead suns. These cosmic tombstones shouldn't have been quaking at all, their nuclear fuel spent billions of years prior. Yet there they were, pulsing with fossilized vibrations, their crystalline cores ringing like struck crystal glasses. The implications rewrote galactic archaeology. White dwarfs cool at predictable rates, acting as cosmic clocks, except Gaia's quakes revealed many were far older than their temperatures suggested. Some showed evidence of planetary debris locked in their atmospheres, the remnants of entire worlds shredded as their dying star expanded. Others wobbled with the gravitational fingerprints of unseen binary companions, hinting at violent stellar divorces long forgotten. Most startling were the blue hook stars, a rare group burning hotter than physics allowed until the quakes exposed their secret. They'd cannibalized helium from neighboring stars, resetting their death clocks in a final act of stellar vampirism. What made Gaia's starquakes revolutionary wasn't just their existence, it was their sheer ubiquity. Over 80% of stars surveyed showed these oscillations, a universal language of vibration cutting across stellar types and ages. For Milky Way historians, it was like discovering every star kept a hidden diary, its pages filled with quakes encoding its birth, its collisions, even its chemical diet. Suddenly, the galaxy wasn't just a static tapestry, it was a living, shivering archive, its stars whispering secrets we'd only just learned to hear. The data also unveiled cosmic violence on scales we'd underestimated. Certain quake patterns pointed to stars born in primordial clusters long since torn apart, their siblings scattered across the galaxy like feathers in a hurricane. Others carried scars of ancient mergers, their vibrations skewed by the gravitational trauma of swallowing another star whole. Even our Sun, Gaia revealed, likely formed not in isolation but as part of a dense stellar nursery, long since dispersed, a fact written nowhere except in the resonant echoes of its distant cousins. Perhaps the most haunting revelation came from the white dwarfs. Their fossilized quakes suggested some had cooled far slower than models predicted, their crystalline cores trapping heat like cosmic thermoses. This wasn't just a tweak to stellar physics, it was a paradigm shift. If white dwarfs age unevenly, then our estimates for the Milky Way's oldest structures, from globular clusters to the galactic halo, might be off by billions of years. The galaxy could be far older than we'd dared to guess, its true history locked in vibrations too faint to notice until now. Gaia's starquakes did more than add detail to our maps, they revealed the Milky Way as a dynamic, trembling entity, its stars still resonating with the echoes of collisions, births, and deaths spanning eons. Every subtle pulse is a sentence in a story we're only beginning to decode, a reminder that even in stillness, the universe is never truly silent. And with Gaia's next data release poised to uncover millions more of these cosmic tremors, one thing's certain: the galaxy's autobiography is being written in quakes, and we've just turned to the first page. From pulsars defying physics to galaxies older than time itself, these 25 cosmic curveballs prove one thing: the universe isn't just stranger than we imagined, it's stranger than we can imagine. Every time we think we've cracked the code, space throws another riddle our way. Dark energy accelerating the cosmos, rogue planets drifting untethered, even a star that dims like a flickering light bulb. Each discovery peels back another layer of the ultimate mystery box. And here's the thrilling part: we've barely scratched the surface. Think about it. A century ago, we didn't know galaxies existed beyond the Milky Way. Half a century ago, black holes were just scribbles in Einstein's notebooks. Today, we're wrestling with quantum ghosts, phantom galaxies, and anomalies that could rewrite the laws of reality. That's the beauty of science. It's not a dusty textbook, but a living, breathing chase. The next jaw-dropping revelation could come tomorrow, from a telescope yet unbuilt or a dataset waiting to be decoded. Maybe it'll be proof of parallel universes, or a signal from an alien civilization, or a particle that unravels dark matter. One thing's certain: when it happens, you'll want to be here to witness it. So keep looking up, stay relentlessly curious, and never stop asking, what if? The universe isn't done surprising us, and neither are we. Hit subscribe to join the next chapter of cosmic detective work, because the greatest discoveries aren't just for scientists in lab coats. They're for anyone who's ever stared at the night sky and wondered. And who knows, the next time science textbooks need rewriting, it might just be your curiosity that helps connect the dots. The cosmos is calling. Don't let the conversation